Throughout this large unit on rotations, divided into two parts in the first and second semester, you may have noticed something. For example, throughout this description of rotations, I've essentially given you another run-through of all of the mechanics that we've looked at thus far. So we've looked at rotational kinematics, rotational dynamics, rotational work and energy. What's next? The rotational version of momentum. So then therefore, let's go ahead and back up to chapter 9 for just a moment and recall the following. Recall the most general way in which we write Newton's second law. The net force applied to an object or applied to a system results in a change in the momentum of the system with respect to time. If we are talking about a distribution of matter or a system of some sort, then the left-hand side of the expression is the following. This is the sum of all of the internal forces that occur between the two objects, or between the objects in question that make up the distribution of matter, plus then the sum of any external forces that may be present. This then results in the change in the center of mass of the system's momentum with respect to time. Recall, however, that the sum of the internal forces that occur between the objects that make up a system through Newton's third law is equal to 0. So then therefore, in general, we write Newton's second law as the sum of the external forces applied to a system. This then results in a change in the center of mass's momentum with respect to time. And then if the sum of the external forces acting on a system equals 0, therefore the change in the momentum of the center of mass of the system with respect to time is equal to 0. Therefore, the momentum of the center of mass is a constant. And then recall, of course, that this situation is referred to as conservation of linear momentum. What is the rotational analog? Well, I'm going to introduce the rotational analog to you in the following way. Okay, so let's ask the question, what is the rotational analog? Okay, let's write Newton's second law in its rotational form as we've seen it thus far. Okay, net torque equals rotational inertia multiplied by alpha, the angular acceleration. Recall, of course, that this expression applies to two situations: the rotation about a fixed axis with respect to an inertial reference frame, or an object that is undergoing a rotation and a translation with respect to an inertial reference frame, as long as the rotation is about an axis passing through the center of mass. Let's now begin to think of this once again in terms of a distribution of matter or a system. So the left-hand side of the expression I'm now going to write in the following way. I'm going to write this as the sum of the internal torques that occur in between the objects that make up the system, plus the sum of any external torques that may be present. This then results in the following quantity. Okay, now just focusing in here on the left-hand side of the expression, the sum of the internal torques that occur between the objects that make up a system is equal to 0. Once again, simply by Newton's third law, the force vectors are equal in magnitude and in opposite directions. So then therefore, if you simply add up the force vectors, you end up with 0. Therefore, the sum of the internal torques is equal to 0. So this is 0 by Newton's third law. And then therefore, the sum of the external torques acting on a system results then in the right-hand side of the expression. But there is a more general way in which we write the right-hand side of the expression, just like there's a more general way in which we write mass times acceleration when talking about Newton's second law in its translational form. What I'm going to do is I'm going to replace the angular acceleration alpha with the derivative of angular velocity with respect to time. Like so. Okay, and now the quantity on the right-hand side of the expression is actually the same thing as this. This quantity right here, because for example, if the rotational inertia of a system is a constant, you would then pull it out of the parentheses here like so, and then you would end up with I times alpha. But there are scenarios in which the rotational inertia of a system in fact can change. We'll see that in some of our basic problems and in some of the basic demonstrations that I'll perform in just a little while. But for now, this new quantity here in the parentheses is given a name. It's referred to as angular momentum. Okay, as we're seeing it thus far, angular momentum is referred to as capital L, by the way, and it's equal to I times omega. It is a vector quantity that ultimately obeys right-hand rule. There is a cross product that is present in all of this. We'll get to that cross product later. But for now, the direction of the angular momentum vector is the same as the direction of the angular velocity vector, omega. So if you have an object like a turntable, for example, or something like that that's rotating in this manner, then the angular momentum vector, L as it's called, points in the direction of our thumb. Once again, it ultimately obeys right-hand rule. Now this is a new quantity here, so let's go ahead and check the units. We have, first of all, the units of the rotational inertia I, which is kilogram meter squared, and then we're multiplying it by radians per second, which is, in terms of the units, just per second. So then therefore we leave it at like that. Those are the units here in metric SI units, that is, for angular momentum. Okay, now going back up to the top board for just a moment, what we have here then is the following. The sum of the external torques acting on a system results in a change in the angular momentum of the system with respect to time. Like so. And then we'll begin to examine scenarios, for example, where the left-hand side of the expression, the sum of the external torques is equal to 0. So if the sum of the external torques is equal to 0, then the right-hand side of the expression is equal to 0, which then means that the quantity L, the angular momentum of the system, is a conserved quantity. Therefore, L is equal to a constant. This situation is referred to as conservation of angular momentum. Now, before I demonstrate this for you, how can you start to get a handle on exactly what is meant by angular momentum? Well, recall how Newton himself described linear momentum. He thought of it as the total quantity of motion of an object or a system. The total quantity of motion, P, is equal to a combination of mass times velocity, the inertial mass of the object or the system multiplied by the velocity of the object or the velocity of the center of mass of the system. That is then what we thought of as the total quantity of motion. This is the angular equivalent. Think of angular momentum as the total quantity of rotation of a system or of an object. So picture L as a description of the total quantity of rotation of a system. So in terms of how we're seeing it thus far, I times omega, the total quantity of the rotation of a system depends upon the rotational inertia I, not just the mass itself, but how the mass is distributed about the axis of rotation and how quickly the rotation occurs, the angular velocity omega. Okay, now let me go ahead and demonstrate this quantity here to you, and I'm also going to demonstrate its conservation. I'm going to show you some demonstrations. In order to do so, I have to tilt my phone, so bear with me as I do. So let me do the following. Okay, and then I have a stool there, and I also have a bicycle wheel, which I'm actually going to move off to the side for now. And then I have these two large weights. Each one of these weights here, by the way, is 2 kilograms. 2 kilograms is about 5 pounds. Okay, now I'm going to go ahead and sit here on the stool. The stool, as you can see, can rotate, by the way, like so. And I'll go ahead and then pick my feet up off the floor, like so. Okay, when I do, acting upon myself and the stool as a system are 2 external forces, the normal force upwards and the force of gravity downwards. Okay, those forces, of course, just cancel each other out because my acceleration is equal to 0. Let's assume that those two forces, the normal force upwards and the force of gravity downwards, occur along the axis of rotation. So then therefore, if they do occur along the axis of rotation, there is no torque due to either of those two forces. The reason for that is because the moment arm R in R cross F is equal to 0 if those forces are applied along the axis of rotation. So we're simplifying the situation here a little bit perhaps. Of course there's friction too, but we're going to ignore that. So then therefore essentially what we're saying is that the sum of the external torques is equal to 0. If the sum of the external torques is equal to 0, this then means that the angular momentum of the system L is going to be a conserved quantity. Okay, now here's what I'm going to do. I'm going to hold my hands out like so, thereby giving me a large value of rotational inertia, mr squared. And then what I'm going to do is I'm going to kick off the floor, so that's going to be an external force, that's going to be an external torque, and I'm going to spin myself up to uniform circular motion, and then I'm going to let go of the floor. And then watch what happens, for example, as I do. Okay, so I'm doing the following like so. Take my feet off the floor and then do this. Hold my arms out. Do this. And so on. Okay, so what was occurring in this demonstration? Let me set these down. Well, first of all, after I spun myself up and I was holding my arms out as I did, I took my feet off the floor and I thereby give myself a large angular momentum vector, L naught, we'll call it. That points in this direction, like so, as I was rotating like this. However, because the sum of the external torques acting on me is equal to 0, that L naught is a constant the whole time. When I pull my arms in, for example, those are internal torques that occur in between the system itself, and the sum of the internal torques is equal to 0. In other words, we don't have to worry about them. It's the external torques that are important. So then therefore, the total quantity of rotation, I omega, is a conserved quantity. So when I hold my arms out like so, and I had a relatively small omega as I was rotating, I would then have an angular momentum, L naught, equal to I naught times omega naught. However, once I pull my arms in, it's going to be the same exact angular momentum as before. It's going to be the same L naught, but in this case, I decrease the rotational inertia I when I pulled my arms in. So if I decrease the rotational inertia, what then has to happen to my omega? It has to increase such that the product I omega is a constant the whole time. Now, of course, you've seen this before with like Olympic figure skaters, for example. When the skater pulls his or her arms in, you see their rotation increase appropriately. This is, of course, ignoring a little bit of friction that occurs between the skaters and the ice, or in my case, the friction that occurs between the stool and the floor. Okay, now here's basically another version of the exact same thing, and that involves, for example, this bicycle wheel. So I can actually do a couple of different demonstrations with this bicycle wheel. First of all, what I'm going to do is keep my foot on the floor to prevent myself from rotating. This then represents an external torque. We're going to ignore that in a few moments. Let me go ahead and spin the bicycle wheel up like so. And then I'm going to take my feet off the floor like this. And right now the bicycle wheel is rotating in this direction like so, giving me an initial angular momentum vector. Watch what happens when I tip over the bicycle wheel. I start rotating like so. Okay, let me put my foot on the floor and then come back to where I was originally. Here's what's occurring in this demonstration. I spin up the bicycle wheel and I give myself an initial angular momentum vector, L naught we'll call it once again, that points like this. And then I tip over the bicycle wheel like so, and I rotate in this manner. When I tip over the bicycle wheel, and it is then therefore rotating like this, it has an angular momentum vector that points downwards. Therefore, I have to rotate like this, such that my angular momentum vector adds to that of the bicycle wheel to give me a total angular momentum vector that points upwards, just like I had it originally when the bicycle wheel was initially spinning like so. So I've got here an L naught, we'll say like this. And then I tip it over like so. And then I've got like an L1 plus an L2 for me rotating. That gives me the same L naught as before, the same angular momentum as before, because once again, the sum of the external torques acting on the system is equal to 0. Okay, here's another version of basically the exact same sort of demonstration. Once again, picking my feet up off the floor. Okay, now what I'm going to do is I'm going to start at rest, and then I'm going to start to spin up the bicycle wheel. And as I spin up the bicycle wheel, watch what happens to me on the stool. Notice that I start rotating like that. In this case, because I start like this at rest, the total angular momentum of the system is 0, and it has to be 0 the whole time. So if I start spinning up the bicycle wheel such that it starts rotating like that, then myself on a stool, I have to start rotating like this, such that the sum of the two vectors, that of the bicycle wheel plus that of me and the stool, like so, adds up to 0 the whole time. Once again, this is ignoring some friction that occurs between the axis of rotation and the stool and so forth, and with the floor as well. So that's a nice demonstration and a nice introduction to this new quantity called angular momentum. Once again, think of it as the total quantity of rotation of the system. Okay, with my demonstrations that I just did here, in the next video, we'll start to take a look at some basic examples.